In this video, I'll be breaking down the February-March 2024 paper 62, that's probability and statistics 2. Now, before we get into the video, make sure to leave a like and subscribe for more videos like this, and comment down below which paper would you like to see me break down next. Let's get into it. Number 1. The length x centimeters of a sample of 100 insects of a certain type was summarized as follows. We've got n is equal to 100, summation of x is 36.8, and summation of x squared is 17.34. Part A. Calculate unbiased estimates for the population mean and variance of x. Okay, so our unbiased estimate of mean, we'll call that mu hat. That's the summation of x over n. So mu hat is equal to 36.8 over n, which is 100. Mu hat is equal to, let's punch that into the calculator, that is 36.8 divided by 100. And this gives us 0.368. Okay, and we also need to get the unbiased estimate for our variance. So that's s squared is equal to 1 over n minus 1, and this is summation of x squared minus the summation of x squared over n, and then we close our bracket. So let's substitute into that formula. S squared is equal to 1 over, that is 100 minus 1, which is 99, and then our summation of x squared is 17.34 minus our summation of x, which is 36.8, and that is squared divided by 100. Let's close our bracket. S squared is equal to, let's punch this into the calculator, 1 over 99 multiplied by 17.34 minus, this is 36.8 squared over 100, and this gives us 0.0384, correct to 3 significant figures, and these are our unbiased estimates for population mean and variance of x. Part B. State a necessary condition for the estimates found in Part A to be reliable. Okay, so for our estimates to be reliable, this sample of 100 insects must be unbiased. So in other words, our sample must be random. So we can conclude that sample must be random. If it's biased, our sample will not be reliable. It will not be representative of the actual population. Number 2. A random sample of 250 people living in Barapet was chosen. It was found that 78 of these people owned a BTEC phone. Calculate an approximate 98% confidence interval for the proportion of people living in Barapet who own a BTEC phone. Alright, so we are looking for a 98% confidence interval. Alright, and since we are dealing with proportion, the formula that we'll use is PS plus or minus Z times the square root of PS QS, and this is all over N. Now this formula is not in your MF19, so you should know this formula by heart. So make an effort to memorize this. Okay, and so this PS represents the proportion of successes, and that would be 78 successes out of 250 people. So 78 out of 250 plus or minus Z, which we will evaluate just now. And so that's proportion of successes, 78 over 250 multiplied by QS, which is the proportion of failures. And if you punch that into your calculator, you get 86 over 125. And this is O over N. N is our sample size, and that is 250. 250. Okay, now we need to find what our value for Z is. we are dealing with a 98% confidence interval, and when we're talking about a confidence interval, we're looking for the area that is in between. So that means the area on these sides is equal, so that's 1%. And so if we want to find what the z value here is, we've got 98% plus 1% to our left, so we can find arc phi of 99%, which is 0.99. So it just means we are reading our tables in reverse to get the z value for a probability of 0.99. And if you do that, you'll find that your z value is 2.326. So this becomes 78 over 250 plus or minus 2.326 multiplied by the square root of 78 over 250 multiplied by 86 over 125, and this is all over 250. Alright, so let's punch this into the calculator. We'll start with the lower bound, 78 over 250 minus 2.326 multiplied by the square root of 78 over 250 multiplied by 86 over 125, and this is all over 250. And so this gives us a lower limit of 0.24244 correct to 3 significant figures, and then our upper limit, which is just substituting the positive sign, you get 0.380. Okay, and this would be our confidence interval. Part B. Manjit claims that more than 40% of the people living in Parapet own a BTEC phone. Use your answer in Part A to comment on this claim. So what we have to do is to compare this 40% to our confidence interval. So 40% is the same as 0.4. Now if we go to our confidence interval, we'll note that 0.4 does not lie within our interval. So using our confidence interval, his claim is not supported. So we can say that it is unlikely. Manjit's claim is unlikely since 40% or 0.4 does not lie within our confidence interval. Let's move on to number 3. In a certain lottery, on average, 1 in every 10,000 tickets is a prize-winning ticket. An agent sells 6,000 tickets. Part A. Use a suitable approximating distribution to find the probability that at least 3 of the tickets sold by the agent are prize-winning tickets. So we know that this is a binomial distribution because we can see our probability of success being 1 in every 10,000 and our number of trials is 6,000. So let's say x is our random variable, and that is number of prize winning tickets. Number of prize winning tickets. And our parameters, x follows a binomial distribution and n is the 6,000 over here. 6,000, and the probability of success 1 in 10,000, so 1 over 10,000. Alright, and so now they're saying use a suitable approximating distribution to find the probability that at least 3 of the tickets sold by the agent are prize winning tickets. Okay, so you should know that from here we're going to move to a Poisson distribution, but you can always check whether that is justified. So to check, we'll calculate NP. NP is 6,000 multiplied by 1 over 10,000 and that gives us 0.6, and this is less than 5, and n is equal to 6,000, which is greater than 50. These conditions actually satisfy a Poisson approximation to the binomial distribution. You should know that as well. Binomial. Alright, so we can say that x follows a Poisson distribution with lambda. In this case, our lambda will be equal to np. So x follows a Poisson distribution, and the lambda here, np, we calculated to be 0.6. Okay, so the question wants us to find the probability that at least 3 of the tickets sold by the agent are prize winning tickets. So we are required to find the probability that at least 3, so that's greater than or equal to 3. Since the binomial distribution is discrete and Poisson distribution is discrete, there is no need for any continuity correction. Okay, so to solve this, we're going to say 1 minus the probability that x is less than 3. Okay, so this would become 1 minus e to the negative lambda, which is 0.6, and then we'll do 0.6 to the power 2 over 2 factorial, and then we've got 0.6, and then we've got 1. Alright, and so let's punch this into the calculator. That is 1 minus e to the negative 0.6 multiplied by 0.6 squared over 2 factorial plus 0.6 plus 1, and this gives us 0.0231, which is our final answer. Now part B says justify the use of your approximating distribution in this context. Okay, so let's just show that over here. That's np which is equal to 6,000 times 1 over 10,000 is equal to, that's 0.6, and we say this is less than 5, and n is equal to 6,000, which is greater than 50, hence Poisson approximation to binomial distribution. Okay, and this would be our final answer. Number 4. Each year a transport firm uses X liters of gasoline and Y liters of diesel fuel, where X and Y have the independent distributions. X follows a normal distribution 10,700, 950 squared, and Y follows a normal distribution with 13,400 and 1,210 squared. Part A. Find the probability that in a randomly chosen year the firm uses more gasoline than diesel fuel. So gasoline is X, and we're saying they use more gasoline than diesel fuel, so X is greater than Y, and we have to find this probability. So what I'm going to do is I'm going to bring the Y to the left hand side, so this becomes probability of X minus Y is greater than 0. I'm going to say let D equal X minus Y, just to make it a bit clearer. We need to find our expectation of D. Okay, so the expectation of D is equal to the expectation of X minus the expectation of Y. Expectation of X is 10,700 minus the expectation of Y being 13,400. So the expectation of D is equal to, let's punch that into the calculator, 10,700 minus 13,400, and that gives us negative 2,700. And then we need to find the variance of D. So the variance of D is equal to variance of X plus variance of Y. Remember that the variance cannot be negative, we always add our variance. So even though we have a negative sign here, we're going to add the variance of y. Okay, so that's 950 squared plus 1210 squared. 950 squared plus 1210 squared. So the variance of d is equal to, that's 950 squared plus 1210 squared. This gives us a very large number of 2,366,600. Since d is based off of two normal distributions, it means d itself must also follow a normal distribution, and its mean is negative 2,700 and its variance is 2,366,600. And remember, we are evaluating the probability that x minus y is greater than 0, and we said x minus y is d, so the probability that d is greater than 0. Now we can proceed to standardizing. That becomes the probability that z is greater than 0 minus 2,700, so that's plus 2,700, and this is all over the square root of 2,366,600. Alright, let's punch this into the calculator. Z is greater than 2,700 over the square root of 2,366,600, and this gives us 1.755. Okay, and we know that this simplifies to 1 minus 5, 1.755. Okay, so this is 1 minus, we can read off the value of phi of 1.755 from our normal distribution tables, and that value is 0.9603. Okay, so now let's punch this into our calculator. That becomes 1 minus 0.9603, and this gives us a final answer of 0.0397. The costs per liter of gasoline and diesel fuel are $0.8 and $0.85 respectively. Part B. Find the probability that the total cost of gasoline and diesel fuel in a randomly chosen year is between $20,000 and $22,000. Okay, so our variables x and y represents the amount of diesel fuel and gasoline fuel that the transport firm uses in a year. Alright, and now we are given the costs for each type of fuel. So for gasoline is being represented by x. We can say that this is 0.80x plus diesel fuel, which is 0.85y, and x here is representing the amount of gasoline they are using per year, and y is the amount of diesel fuel they are using per year. If we multiply the respective variable by the price, we then get the total values for our fuel per year. Alright, so I'm actually going to combine this to one variable called t. So t is equal to 0.80x plus 0.85y. Alright, we need to find the expectation of t. Expectation of t is equal to 0.80 times the expectation of x. The expectation of x is in our stem, that's 10,700, and then plus 0.85 times the expectation of y. The expectation of y is 13,400. Alright, so that is 13,400. So expectation of t is equal to, let's punch this into the calculator, that's 0.80 times 10,700 plus 0.85 times 13,400, and this gives us 19,950. Now let's find the variance of t. So this will be 0.80 squared times the variance of x. The variance of x is 950 squared. 950 squared plus our 0.85 squared multiplied by the variance for y. The variance for y is 1210 squared. 1210 squared. Alright, so let's simplify this. Punch this into the calculator. That's 0.8 squared multiplied by 950 squared plus 0.85 squared multiplied by 1210 squared, and this gives us, that is 1,635,412.25. Alright, again, t is a variable that is based off of x and y, which both follow a normal distribution. So as a result, t also follows a normal distribution, and its mean is 19,950. Its variance is 1,635,412.25. Alright, and we need to find the probability. That the total cost of both fuels is between $20,000 and $22,000. Okay, so the probability that t is between $20,000 and $22,000. Alright, so now let's standardize. That becomes 20,000 minus 19,950, and this is over the square root of 1,635,412.25. okay, and then we have z here. Then we have 22,000 minus 19,950, and this is all over the square root of 1,635,412.25. okay, so let's punch this into the calculator and simplify. That is 20,000 minus 19,950, and this is all over the square root of 1,635,412.25. that gives us 0.039. okay, and that's less than z, which is less than. Let's substitute in 22,000, and that gives us 1.603. okay, so if we're to sketch a bell curve, 0 would be somewhere here, and our first value, that's 0.039, and then we've got our second value, that's 1.603, and the region that we're looking for is over here. So to find that region, we can say phi of 1.603 minus phi of 0.039. Let's read off both values from our normal distribution tables. So phi of 1.603 is 0.9455 minus phi of 0.039, which is 0.5156. okay, so if we punch this into our calculator, that's 0.9455 minus 0.5156, and this gives us 0.42, or that's 430. So therefore our final answer here is 0.430 0, correct to 3 significant figures. Number 5. A teacher models the numbers of girls and boys who arrive late for a class on any day by the independent random variables. G follows a Poisson distribution with lambda 0.10 and B follows a Poisson distribution with lambda 0.15 respectively. Part A. Find the probability that during a randomly chosen 2-day period no girls arrive late. Okay, so we're going to say let T be the random variable, number of girls who arrive late on a 2-day period. Okay, and T must follow a Poisson distribution, but notice that these distributions from the stem of the question are actually defined for 1 day, and in this case we are required to evaluate for a 2-day period. So we're going to multiply this 0.10 by 2 so that it satisfies our interval of 2 days. So that would become 0.20, that's our lambda. And we want to find the probability that no girls arrive late. So that's the probability that T is equal to 0, and that's equal to e to the negative 0.20. Let's punch that into the calculator, simplify it, and give it correct to 3 decimal places. That gives us 0.819, and that's our final answer. Let's move on to part B. Find the probability that during a randomly chosen 5-day period the total number of students who arrive late is less than 3. Okay, so we need to combine the distributions for the boys and the girls, and I'm actually going to call that distribution S. So S is the sum of G, which is girls, plus boys, and that gives us the total distribution. And we need to find lambda, and we can simply add the lambda for G to the lambda for B. But we also have to consider that here we're dealing with a 5-day period, and like I said, our original distributions are for only 1 day. So we're going to multiply each by 5 days. Okay, so 5 times the lambda for the girls, that's 0.10, plus 5 times the lambda for the boys, which is 0.15. So the lambda for S, lambda is equal to 5 times 0.10 plus 5 times 0.15. That gives us 1.25. I should have defined S being the random variable, total number of students who arrive late on a 5-day period. Okay, so because S is made up of G and B, which both follow a Poisson distribution, it means S also follows a Poisson distribution, and its lambda we evaluated to be 1.25. So now we can find the probability that the total number of students who arrive late is less than 3. So that is the probability that S is less than 3. So that's equal to e to the negative 1.25, and that's 1.25 squared over 2 factorial plus 1.25 plus 1. So the probability that S is less than 3 is equal to, let's punch that into the calculator, that's e to the negative 1.25 multiplied by 1.25 squared over 2 factorial plus 1.25 plus 1, and this gives us 0.868, and that is our final answer. Let's move on to part C. It is given that the values of the probability that G is equal to R and the probability that B is equal to R for R is greater than or equal to 3 are very small and can be ignored. Find the probability that on a randomly chosen day, more girls arrive late than boys. Okay, so let's evaluate the possible scenarios in which more girls arrive late than boys. Alright, so let's start with, we could have 1 girl and 0 boys arriving late, or we could have 2 girls and 0 boys, and we could also have 2 girls and 1 boy arriving late. Okay, and now we can't go beyond 3 girls because we're told that values for R is greater than or equal to 3 are very small and can be ignored. So let's evaluate each of these scenarios. So the probability of having 1 girl arriving late, that's the probability that G is equal to 1 multiplied by, we're using the AND rule, multiplied by the probability of 0 boys, so B is equal to 0. Okay, so the probability of 1 girl arriving late is E to the negative, what is lambda for the girls? That is 0.10, 0.10, okay, and this is being multiplied by lambda 0.10, and this is also, let's put this in a bracket of its own, this is also being multiplied by the probability of 0 boys arriving late, and that's E to the negative 0.15. So let's punch this into the calculator. That is E to the negative 0.1 multiplied by 0.1 multiplied by E to the negative 0.15, that gives us 0.078, or that's 0.77880. Let's move on to the second scenario. That's the probability of 2 girls arriving late times the probability of 0 boys arriving late, and so this is equal to E to the negative 0.1 multiplied by, that's 0.1 to the power 2 over 2 factorial, and this is being multiplied by, again, E to the negative 0.15. Let's punch this into the calculator. That is E to the negative 0.1 multiplied by 0.1 squared over 2 factorial, and this is multiplied by E to the negative 0.15, and this gives us, that is 0.0038940. And let's evaluate our third scenario. That's the probability of 2 girls arriving late and 1 boy arriving late. Okay, so this is E to the negative 0.1 multiplied by, that's again 0.1 squared over 2 factorial, and this is multiplied by E to the negative 0.15 multiplied by 0.15. Okay, let's punch this into the calculator. This is E to the negative 0.1 multiplied by 0.1 squared over 2 factorial multiplied by E to the negative 0.15 multiplied by 0.15, and this gives us, that is 0.000, and we've got 54810. Alright, now to get our probability, we can sum up the probabilities of all three scenarios, and so that is 0.0077880 plus 0.003890 plus 0.00054810. Let's punch that into the calculator. 0.077880 plus 0.003890 plus 0.00054810, and this gives us a total probability of 0.0823, and this is our final answer. Following a timetable change, the teacher claims that on average more students arrive late than before the change. During a randomly chosen 5-day period, a total of 4 students are late. Part D. Test the teacher's claim at the 5% significance level. Alright, so we need the distribution for the total students which we created earlier. This is our distribution S over M. We know that S represents the total number of students who arrive late on a 5-day period, and that actually matches what we have in part D, but I just want to take what we have over here. That's S follows a Poisson distribution, and lambda is 1.25. Right. We're saying test the teacher's claim at the 5% significance level. Alright, so to be able to do that, we first need to state our null and alternative hypothesis. So lambda, the alternative hypothesis is that lambda is 1.25, and H1, the teacher is saying that on average more students arrive late, so lambda is now greater than 1.25 according to the teacher. Alright, so we are carrying out this test at the 5% sig level. Okay, and we can create our rejection rule. Reject H0 if the probability that is, which is this is an upper tail test, so greater than or equal the critical value if this is less than our significance level, which is 0.05. Alright, so this value will be our test statistic, which we are given to be 4 students are late on a 5-day period. So let's evaluate that. The probability that S is greater than or equal to 4. This is equal to 1 minus the probability that S is less than 4. And so this is 1 minus e to the negative, lambda is 1.25. And so we've got 1.25 to the power 3 over 3 factorial plus 1.25 squared over 2 factorial plus 1.25 plus 1. And this is all equal to, let's punch this into the calculator. 1 minus, this is e to the negative 1.25, and so we've got 1.25 cubed over 3 factorial plus 1.25 squared over 2 factorial plus 1.25 plus 1. Let's close our bracket, and so this gives us 0.038, that is 383. Now let's compare our answer to our significance level. 0.0383 is in fact less than 0.05. So this means that this value over here actually lies within our rejection region. So we can conclude that reject H0 in favor in favor of H1 which is the teacher's claim. And now let's conclude in context. There is evidence at the 5% SIG level that the number of students arriving late has increased. So teacher's claim is justified. Teacher's claim is justified. Alright, and this would be our final answer. Number 6. The graph of the probability density function f of a random variable x is symmetrical about the line x is equal to 2. It is given that the probability that x is between 2 and 5 is equal to 117 over 256. Part A, using only this information, show that the probability that x is greater than -1 is equal to 245 over 256. Okay, so we're given that we have a probability density function that is symmetrical about the line x equals 2. So I'm just going to create a rough sketch. Obviously, we don't know what shape it is. We don't know what sort of function it is. But I'm just going to assume here that we have a quadratic. So it would look like this, and it is symmetrical about the line x is equal to 2. It doesn't matter what shape you use as long as it is symmetrical about x is equal to 2. Alright, and then we're given that the probability that x is between 2 and 5 is 117 over 256. So 5 would probably be somewhere here. And we're saying this region between 2 and 5 is equal to 117 over 256. And they're asking us to prove that the probability that x is greater than -1 is equal to 245 over 256. Okay, so -1 would actually be somewhere here, -1. And since this is symmetrical, we know that from 2 to 5 there are 3 units. So if we move backwards from 2 to -1, we also have 3 units, meaning that the area between -1 and -2 should be the same as the area between 2 and 5. So this region over here, I'm going to shade that in, let's do this lighter shade of blue. Right, this region over here is also 117 over 256. Okay, but now what we want is the probability. Let me go back to our blue. The probability that x is greater than -1. So if I can just erase this shading here, just so that we can quickly see what we are looking for. The area that we are looking for, I'll shade it in red, is greater than -1. So it's all of this area, right? And what you will notice is that this area is the region from -1 to 2, and then from 2 to the rest of the function. Alright, so we know that from -1 up to 2 it is 117 over 256, 117 over 256, and then we also need the area from 2 to the rest of, or to the end of our function. We know that our function is symmetrical about the line x equals 2, so that must mean x splits our function into 2 equal parts. So from 2 to the end of our function, this region must actually be equal to 0.5. So we can add that 0.5, I'll write it as half, just so that we are consistent with the use of fractions here. So that is equal to 117 over 256 plus 1 over 2 and that gives us 245 over 256, and that's our final answer. Alright, so moving on to part B, it is now given that for x in a suitable domain, f of x is equal to k times 12 plus 4x minus x squared, where k is a constant. Find the value of k. Okay, so we are now given our function and it turns out to be a quadratic. To evaluate k, we can use the information that we're given in the stem of the question. We were given this, the probability that x is between 2 and 5 is equal to 117 over 256. We can integrate our function f of x from 2 to 5 and then equate it to 117 over 256. I'm going to take k outside the integral, and then we've got 12 plus 4x minus x squared. With respect to x, this should be equal to 117 over 256. Okay, so let's integrate. So that's k, open bracket. If you integrate 12, you get 12x, and then you've got 4x squared over 2 minus x cubed over 3, and this is all equal to 117 over 256. Oh, and I forgot to add our limits over here. That's from 2 to 5, so we can simplify this. That's k 12x 4 over 2 becomes 2x squared minus x cubed over 3 from 2 to 5. This is equal to 117 over 256. Now let's substitute in our limit. So that becomes 12 times 5 plus 2 times 5 squared minus, that's 5 cubed over 3, and then our lower limit, that's 12 times 2 plus 2 times 2 squared minus 2 cubed, and this is over 3. Okay, and this is all equal to 117 over 256. Right, so let's punch that into a calculator. 12 multiplied by 5 plus 2 times 5 squared minus 5 cubed over 3, and then minus 12 times 2 plus 2 times 2 squared minus that 2 cubed over 3, and then we close our bracket, we get 39. So this is 39k, and that's equal to 117 over 256. Alright, so we can say that k is equal to 117 over 256 divided by 39. So k should be equal to, punch that into the calculator, 117 over 256 divided by 39, that gives us 3 over 256, and this is our final answer. Part C. A different random variable x has probability density function g of x is equal to 2 over 9 times 2 plus x minus x squared. The domain of x is all values of x for which g of x is greater than or equal to 0. Find var of x. Alright, so we need to find the limits for our PDF g of x, and we were given the information that the domain of x is all values for which g of x is greater than or equal to 0. So let's solve that inequality. G of x is greater than or equal to 0. That's 2 over 9 times 2 plus x minus x squared is greater than or equal to 0. We can omit the 2 over 9, so 2 plus x minus x squared is greater than or equal to 0. This is a quadratic inequality. Now I'm just going to multiply through by -1 because I don't like working with negative quadratics. So this becomes x squared minus x minus 2, and our sign changes because we've multiplied through by -1. This is less than or equal to 0. Alright, so let's find our roots. X squared minus x minus 2 is equal to 0. That will factorize to give, we've got x minus 2 plus 1. So x is equal to 2 and x is equal to -1. If we quickly sketch our curve over here, this would be our x-axis and our roots are -1 and 2. We are looking for the less than or equal to region, so that's the area below the x-axis. So that means our domain is x is between -1 and 2. So we can now go on to find our variance of x. So our variance would be, we're going to take the 2/9 outside from our function. Remember, we're integrating our function. So from -1 to 2, and our function is being multiplied by x squared using the formula from the MF19. Our function is 2 plus x minus x squared, and then we are supposed to subtract our mean. Okay, so let's just sketch a diagram of our PDF so that we see what our mean would be. It is a negative quadratic, so it's an N-shaped curve like this, and we said our roots are -1 and 2, so that's -1 over here and that's 2, and so our mean would actually be the midpoint of 2 and -1. So that's 2 minus 1 over 2, which gives us 0.5. So our mean would be 0.5, and this is with respect to x, and then we subtract our mean 0.5 squared, which we have deduced from our curve over here. Alright, so now let's expand 2/9, the integral from -1 to 2. That becomes 2x squared plus x cubed minus x to the 4 with respect to x, minus this becomes 0.25. And now we can proceed to integrate. We've got 2/9, 2x squared will become 2/3x cubed, and then we've got x to the 4/4 minus x to the 5/5, and our limits are -1 and 2, and we're subtracting the 0.25. Alright, we can proceed to substitute in our limits. So that's 2/9, and we'll start with our upper limit, 2/3 times 2 to the power 3 plus 2 to the 4/4 minus 2 to the 5/5. And now let's move on to the lower limit. That's 2/3 times -1 cubed plus -1 to the power 4/4 minus -1 to the 5/5, and we're still subtracting the 0.25. Alright, so let's simplify this. We've got 2/9, and then if we simplify what's inside the bracket, that's 2/3 times 2 cubed plus that's 2 to the power 4/4, and then we have minus, that is 2 to the power, that's 5/5, and then we close our bracket, minus, that's 2/3 times -1 to the power 3 plus that's -1/4, and then we have minus, that is -1 to the power 5, and this is over 5. Let's close our bracket. This gives us 63/20 minus 0.25. So let's simplify. 2 over 9 times 63 over 20 minus 0.25. That gives us a final answer of 9 over 20. Number 7. The heights in centimeters of adult females in Lithuania have mean mu and standard deviation sigma. It is known that in 2004 the values of mu and sigma were 163.21 and 6.95 respectively. The government claims that the value of mu this year is greater than it was in 2004. In order to test this claim, a researcher plans to carry out a hypothesis test at the 1% significance level. He records the heights of a random sample of 300 adult females in Lithuania this year and finds the value of the sample mean. Part A. State the probability of a type 1 error. We are not told the distribution. However, since we know that our sample size 300 is greater than 30, we could still use the central limit theorem to assume that we're working with a normal distribution. And when we're doing hypothesis tests for a normal distribution, we know that our type 1 error, the probability of a type 1 error, is the same as our significance level. So in this case, the probability of a type 1 error is equal to 0.01. Don't write it as a percentage, write it as a decimal. Okay, now we are told that you should assume that the value of sigma after 2004 remains at 6.95. Part B. Given that the value of mu this year is actually 164.91, find the probability of a type 2 error. Alright, so before we even evaluate the type 2 error, let's break down everything so that it makes sense. So let x be our random variable, and x represents heights in centimeters of adult females in Lithuania. Alright, and our h0, our now hypothesis is that mu is equal to 163.21, and our alternative hypothesis is the government's claim. The government claims that the value of mu this year is greater than it was in 2004. So they're saying that mu is greater than 163.21. Alright, so now at this point, assuming that h0 is true, this allows us to use a mu of 163.21, and using the central limit theorem like I mentioned earlier, we can now assume that the sample mean x bar follows a normal distribution since n here is actually greater than 30. So that means our mean would be 163.21. So this would be 6.95 squared over root n being 300. Okay, so we've got an upper tail test at the 1% significance level, sig level. Alright, so if we were to sketch a bell curve for that, it would look like this. This is the 1% significance level. Alright, our z value here would be 2.326. Alright, so we can then create a rejection rule that says reject h0 if z is greater than 2.326, because that would mean your z value lies in the rejection region. Alright, so this is the information we have been given in the question. Now they've said that given that the value of mu this year is actually 164.91, find the probability of a type 2 error. Alright, so we've had a change or a correction into our mean, so we need to find the probability of a type 2 error. To be able to do that, I'm going to sketch another curve over here. We need to find the critical value over here. So in this case, this value over here is the z value that you have when you standardize. But to calculate our type 2 error, we need to know the critical value. So we can say C minus the original mean that we had before the correction. That's this 163.21, 163.21 over our standard deviation. Our standard deviation would then be 6.95 over root 300. Oh, that means I made a mistake over here. That square root sign that we have over here should not be there. This should just be simply 300. Alright, okay, so we are saying that C minus 163.21 over 6.95. Okay, and this is all equal to 2.326, which is the Z value. We are trying to reverse the process of standardization so that we can get the critical value C, and once we have that critical value, we can determine the probability of being in the acceptance region or the probability of a type 2 error. Alright, so this becomes C minus 163.21 is equal to 2.326 times 6.95 over root 300, and so C is equal to, that's 2.326 times 6.95 over root 300 plus the 163.21. Okay, so our C here is equal to, that's 2.326 multiplied by 6.95 over root 300, and then let's add the 163.21, and so this gives us C is 164.14. Okay, so now that we have our value for C, let's come and write it over here. Our value for C is 164.15. So we want to find the probability of landing in this region that is unshaded with our corrected mean. Okay, so the probability of being in this region would be the probability that our sample mean is less than this value. So the probability that x bar is less than 164.14, given that our mean is the corrected mean. What is our corrected mean? 164.91 over here. Alright, so that is 164.91. so that we can standardize. This becomes Z is less than 164.14 minus our corrected mean here, 164.91, and this is all over our standard deviation, which is 6.95. It's still the same, over root 300. Probability that Z is less than, let's punch this into the calculator, that is 164.14 minus 164.91 over 6.95 over root 300. Alright, and so this gives us negative 1.91, that's 9. and we can write this. Do we still have space? Let's write it on the side. This is the same as 1 minus phi of 1.919. So that's 1 minus, let's read off the value for phi of 1.919 from our normal distribution tables. That is 0.9724. Alright, so if we simplify that, that's 1 minus 0.9724. That gives us 0.0276, and we can conclude that therefore our final answer is 0.0276. So that's it for this paper. If you found it useful, please leave a like and subscribe, and comment down below which paper would you like to see me break down next. Bye bye.